covering enzymes, water, acids, and bases. So let's go ahead and hop into our learning outcomes. So today we want to look at the notation, basically how we write and how we describe chemical bond formation and chemical reactions. And then we're going to look at the energetics of those reactions, whether they require energy input or whether they give off energy. Then we're going to look at some of the different factors that determine reaction rates. Okay, so how fast do these reactions occur under different circumstances? Then we're going to look at enzymes. We're going to look at what they do, why they're important. We want to take another quick look at water and look at why it's important as a solvent and look at its polarity. And then we're going to look at acids and bases, right? Specifically the concentration of H+ ions in the solution as it relates to the pH scale. And then we want to look at a pH buffer system and look at how your body resists changes inside of pH. So starting with our notation and energetics. What we're going to be talking about is the energetics from chemical energy. Okay, so all the energy that you use in your body is chemical energy, things we get from breaking down bonds between chemicals. All right, so most of this energy, of course, is acquired from food for us, and all of the chemical reactions that are going on in your body are going to fall into two different categories. Right, based on whether they require energy input or whether they give off energy when the reaction happens. So an endergonic reaction, okay, endergonic reactions are going to require an input of energy, okay? So ender, right, is going to require an input of energy for the reaction to proceed. So a reaction that is exergonic, okay, so exergonic, X here, EX, is going to release energy when the reaction proceeds. Okay, so let's look at this kind of in a graphical layout. So here's an example. Here's our graph of what happens in an endergonic reaction. So we're going to start out with our reactants. That's the products that or the things that we're beginning with, the molecules that we're beginning with. And then we're going to have to input energy here into our system. Right, so you can see that this is going to require an input of energy here. And then we're going to create our products. Right? And our products are what we end a chemical reaction with. Right, so endergonic here, you can see we're going to require us to put this energy in. So what's a biological example here of an endergonic reaction, right? One that you should be familiar with. Well, photosynthesis here is the classic endergonic reaction. So inside of photosynthesis, our products here, okay, are going to be here on the left side of our reaction. So we're going to, I'm sorry. I just think I just said that backwards. Let's start this slide over again. So here we have a biological example of an endergonic reaction, and kind of the classic biological reaction for an endergonic reaction is photosynthesis. So let's take a look at photosynthesis. So in photosynthesis, we're going to start with our reactants, and our reactants here are going to be CO2 and water. And then our products that are going to be created are going to be on our right side here, and our products are going to be glucose and oxygen. So this is going to require an energy input to change these low energy products, this CO2 and water, into a high energy product, right, being the glucose, and a byproduct of oxygen. And plants get that massive amount of energy that they have to input into this process from capturing sunlight. Okay, so the sun, right, is going to be, answer the question here, where do the plants get that energy? So now let's flip over and look at an exergonic reaction, and we're going to see that it's just the opposite, right? So an exergonic reaction is going to release energy. Okay, so now as we move from our reactants, right, which was on the left side of our equation here, that's what we started with, and we're going to move to our products, right? Now we're going to get an energy output, okay? And this is going to mark it being an exergonic reaction. So let's look at a biological example of an exergonic reaction. Okay, this is what goes on in our bodies for cellular respiration. Okay? So now we're going to start with that glucose. Let's assume that you ate something sugary or carbohydrates and sugar, and you've taken in the glucose. Now we want to break that glucose down so that we can get the energy from it, that energy release from the exergonic reaction. So we're going to start with our reactants. Okay, so this time our reactants over here are going to be our glucose and our oxygen, right? We eat glucose with our food, we breathe in oxygen from the air. And our products, right, is going to be CO2 and water, and then the energy release, right? So then we're going to exhale that CO2 to get rid of it, right? And then we have the water in our system that we can excrete if we need to. And we've harvested now this energy, right? Tells you there about 686 kilocalories of energy from breaking down this glucose molecule. In all these chemical reactions, I was already using these names, but I didn't exactly define them for you, so I just want to give you a definition here when we're talking about the notation of these reactions. The reactants are what I had on the left side of the equation here, and it's the substances that are entering into the reaction. Sometimes we have some intermediates. I didn't talk about intermediates here, but you might have some intermediate products that are just there temporarily for a short amount of time. And then eventually you'll get into your products, which is your final result, right? The end result of the reaction. Okay? So let's continue this notation and look at a couple of classic chemical reactions. So we're going to have our reactants on the left, we're going to have our products on the right, and we're just going to use some A and B's here to represent basically any types of chemical compounds here, just to kind of use them as a generic form, kind of like you would in algebra. So a decomposition reaction is when we're going to start with two things and they're going to decompose and basically break apart into two individual atoms. So a decomposition is going to start with an AB, and that's going to decompose into A plus B. That is in direct opposition to a synthesis reaction, okay, which is just going to be the reverse of that. So that's going to be starting with an A and adding a B, and then the product is going to be AB together. These reactions can be reversible, right, as you see in the bottom right-hand corner. And to denote a reversible reaction, we're going to put an arrow going in both directions. Okay, if that reaction was not, when we're not doing it, it is not a reversible reaction, we're going to draw a single arrow in the left to right direction, indicating we're going from our reactants to our products. So if this is reversible, and this equation can kind of slide back and forth based on different factors and concentrations and other things that we're going to look at, then it's said to be reversible, and we denote that with the double arrow going in both directions. Another classic reaction that we're going to see is an exchange reaction, and we're going to see that in the bottom left-hand corner there, and that's starting with an AB plus a CD, and then you're going to exchange those, and so then you're going to end with something like AC and then BD. Okay, so here's a couple of examples of reactions for you. Let's replace our A's and B's now and actually put in a couple biological examples here for you. So on top, you're going to see a reversible synthesis and decomposition reaction. Okay, so if we take our carbon dioxide and water, right, we can make a carboxylic acid out of that. Okay, and you're talking about this is how CO2 is transported through your body and through your bloodstream, so it can be excreted at the lungs. Right, so it needs to basically take CO2. In its gaseous form, convert it to something it can move, this carboxylic acid, right? Moves it through your body, and then it converts it back to CO2 for you to exhale. On the bottom, we have an example of an exchange reaction, and here you see what happens if you mix. We have a hydrochloric acid and sodium hydroxide, so we're mixing HCl here with NaOH. And if we have the exchange reaction here, we're going to exchange our OH and put it with the H. That's going to give us H2O. We're going to have water, and then we're going to make NaCl, right, which is basically salt. Okay, and when you mix an acid and base together, that's what you're going to get. You're going to get the production of a salt and water. We have been talking with a bunch of chemistry so far, and chemistry, intro chemistry is a prerequisite for the course. But now we want to kind of focus and move away from just kind of regular chemistry and start to focus on biochemistry. And so biochemistry is that combination of biology and chemistry. And so we refer to it as the chemistry of life. So now we're going to start kind of putting all of the chemistry and the reaction mechanisms that we've looked at in a organic, in a life-based setting. And in that, we're going to find that the chemistry of life involves organic compounds. So an organic compound is a compound that's going to contain carbon that is bonded to hydrogen. Okay. So when you go to take organic chemistry, for example, it's all about these carbon-containing compounds. Inorganic, then, are going to be compounds which do not usually contain lots of carbon, right, bonded to hydrogen. And there's some other examples there, water, acids, bases, salts, right? Those are just some examples of inorganic chemicals. I also want to highlight here, since you haven't had organic chemistry yet, that when we draw these different chemical compounds, and you're going to start to see some of those as we get into macromolecules and stuff in the next lecture, that we don't want to draw out the entire chemical structure because it's just way too complicated and way too much information that we don't really need. So organic chemists have a kind of shorthand version for drawing compounds, and this is the way you're going to see a lot of the compounds presented as we move forward. So just to refresh you on chemistry and make sure that you're not confused about the structures you see, I want you to know and make sure that you understand that these two structures are equivalent to each other, meaning the hydrocarbon chain you're seeing on the left is exactly the line structure that you're seeing on the right. Okay, so how have we reduced that? Well, the way we're going to kind of shorthand this is we're not going to draw any carbons. Okay. What we're going to say is at the intersection of these lines, we're going to assume there's a carbon, okay? So if we go in and we put our carbon in, everywhere that there's an intersection on these lines, we'll see that we have our 6 carbons, okay? The same 6 carbons that we have right here in the center of the compound. And then we assume that if there's not something properly written there, that carbon is filled in with hydrogens, okay? So I could now go back and I could put an H, right, on each one of these. Right, that carbon only had 1 connection. It wants 4, so it needs 3 hydrogens. Right, this carbon should have 2 hydrogens on it. Okay, so you could go through and fill all those in if you wanted to. Right? But instead of having to draw all this and have all these carbons and hydrogens and have all this clutter in the way, it's much easier for us to be able to draw a simple line structure and everybody know exactly what we're talking about and what we're trying to depict without having to draw all the details. Okay, so as you start to see these carbon rings and these other structures coming up, know that all those carbons and all those hydrogens are there. It's definitely still an organic compound. We're just not drawing them for simplicity's sake. All right, so now let's kind of shift gears and start talking about what are the factors that are going to influence reaction rates. Okay, so we've got some reactants. They're going to be converted to products, right? How quickly does this happen? Well, it depends, right? And it depends on a lot of different factors. There are a couple things that have to happen in all chemical reactions. The first thing is the reactants have to come in physical contact with each other, okay? They cannot bond with each other if they don't come into proximity of each other and come into contact, okay? And then the next thing that happens is they must overcome the repulsive force of their electrons, right? So we've got those valence shell electrons, right, going around the outside. We've got those positive and negative charges, right? So if they don't touch each other in the correct orientation, right, if they've both got maybe a positive side and a negative side and the 2 negative sides combined touch each other, they're still going to get repelled, right? So not only do they have to come in contact, they have to come in contact in the right orientation and be able to overcome this repulsive force, right, of bringing electrons near each other, right, which is what's going to happen when 2 atoms come close to each other. So our different factors that are going to influence these reaction rates are down here on the bottom. And so we want to look at concentration, right, of our reactants and products, the temperature the reaction's occurring at, okay, hotter and cold, our different reactant properties, right, solid, liquid, gas, things like that, and then is there a presence of a catalyst, okay? So breaking these down, how does concentration influence a reaction rate, okay? Well, in general, the higher the concentration, the more collisions you're going to have, right? So the faster the reaction rate, okay? So the more the higher the concentration, the more collisions, the faster your reaction rate's going to be, right? Low concentration means fewer collisions, means less probability of two things, coming together in the correct orientation. And so that's going to happen at a slower rate. Now, there's a point where this is all a part of negative feedback, right? There is a point where you can increase the concentration so much that it starts to have a negative effect, right? But in general, especially at lower concentrations, increasing the concentration is going to speed up the reaction. We also need to consider our reactant properties. Okay, so let's talk about something, say, as a solution that's something that is solid. Okay, so reactions that take place inside of a liquid or inside of a solution, right, take place much faster than something in a solid. Okay, why? Once again, it's about number of collisions, right? So things that are molecules that are in a solid, they don't move very far or very fast, right? So their number of collisions is very low, right? So anything that happens in a solid phase is going to have a much slower reaction rate than something that happens in the solution phase. Okay. Also, going back one slide here, let's take a quick look at the rusty car in the lower right-hand corner, right? And think about this as well. Where does rust happen? Okay, so rust is a reaction. It's oxidation of metal, and it happens where air, right, is touching that surface. Okay, does rust happen in the middle of a solid piece of metal? Okay, no, it doesn't. Why? Well, because there's not oxygen that is available in the middle, the solid piece center of the middle, right? So this reaction can only happen on the solid surface at where it comes in contact with air, for example, okay? So that solid phase is going to limit reactions to only happening on the surface because in the interior, nothing is available, right, for reaction. We can also talk about temperature, okay? So when you increase temperature, you increase the amount of kinetic energy in the system, okay? So energy is not created or destroyed, it has to go somewhere. So when you add temperature into the system, you're adding energy into the system, and that's going to result in kinetic energy of the molecules. It means they're going to move faster, okay? So if they are moving faster, so a high temperature means that they're moving a lot faster, okay? If they're bouncing around very speedily, chances are that they run into somebody in the correct orientation goes up, right? The faster the particles are moving around. So that means things that are cold and slow, right, that these particles move slower, and that means that they're going to then have a lower or slower reaction rate in colder temperatures. And then finally, we want to talk about the presence of a catalyst. Okay, so we're going to be looking at enzymes coming up, which are our biological catalyst. But inside all of chemistry, you can have a general catalyst, and a catalyst comes in and speeds up the reaction rate. And it does this by lowering the activation energy that's required for the reaction. So remember on our graph when we were talking about a endergonic reaction, right, requires this energy input into it. A catalyst is going to lower that energy input that is required by making this matching process, right, faster and more energy efficient. So catalysts are going to speed up, right? The presence of a catalyst is going to speed up this reaction rate. So, like I said, in our bodies, our catalysts are enzymes, okay? So enzymes are proteins that are inside of our body, and they want to lower that activation energy down and make this reaction process more efficient so that it happens faster, okay? So how do they do that, okay? Well, they're this reusable protein, and they are highly specific for a particular reaction. And basically, they play matchmaker in this scenario, and they help the reactants find each other in the proper orientation so that they can speed up the reaction and make it much more efficient, right? Which actually requires the energy that's required for it to happen, because you're not wasting energy having things just randomly bump around and not run into each other in the correct orientation. So looking at an enzyme here as a catalyst, on the right we have an example of an enzyme called sucrase. So sucrase is the enzyme, and what it does is it takes sucrose, that's the substrate, that's the reactant that we're going to start with, and it actually breaks sucrose in half into glucose and fructose. Okay, so normally this reaction does not want to proceed. Once sucrose is together, it does not want to break apart. Okay? So if you want to acquire the glucose, say that you've had in your body as sucrose, and you need to break that back apart, having this enzyme available is going to make that a much easier and much more efficient process, and it's also going to speed it up, right? Because it is a biological catalyst. So here's the graphical representation, bringing those graphs back of what we were talking about. Right? So we had our energy of our reactants over here, okay, and we're going to go through a process, and this is the energy of our products, okay. So what we're doing here is this is actually a exergonic reaction, right? We are going to get a release of energy. Ultimately, we're going to get a release of energy when this happens, okay? But first, we have to get over this hump, right? There has to be some energy input to actually break the sucrose apart. And then once we get it broken apart, ultimately, the glucose and the fructose are going to have more energy available than the sucrose did. But the sucrose doesn't want to break, and we got to put that amount of energy in. By adding an enzyme that's going to assist us in this process, instead of having to put in this giant amount of energy, okay, now with the enzyme helping and playing matchmaker and speeding up this reaction, we only have to put in this amount of energy, okay? And so that's going to leave us here, it saved us this amount of activation energy. That's going to make us more efficient, and that's going to make this process happen faster. So just like we had different factors that affected our enzyme reaction rates, we're also going to have factors that influence an enzyme's rate, all right, and its effectiveness. And some of these are going to be the same, but let's take a look at them. So first of all, temperature. So yes, increasing temperature is going to speed up the reaction, right? Whether it's a catalytic reaction, enzymatic reaction, or a non-enzymatic reaction, right? We know temperature is going to increase the reaction rate regardless. However, you have to be particularly careful in enzymatic reactions, because an enzyme is a protein, okay? And since an enzyme is a protein, high temperatures denature, right, or unfold, right, destroy proteins. So you can increase your temperature trying to increase your reaction rate, but if you push it too far, okay, if you're Icarus and fly too close to the sun, right, and your wings melt, right, you can push the temperature too high, you denature your enzyme, and everything is ruined, right? The enzyme ceases to function, the reaction completely fails, okay? So you can push temperature up, but not only to that point. You don't want to get into the breaking point and denature your enzyme. Concentrations are also going to affect reactions with enzymes, just as concentration did those without enzymes, okay? However, let's think about now the negative feedback aspect of concentration. We talked about negative feedback loops earlier, right? And so this idea of negative feedback is that eventually putting in so much reactants, or even if the reaction's been running a long amount of time and there's a high concentration of products now, either way, there's a point at which this begins to hinder the reaction. Okay, so if you've got all these reactants and they're revolving around, right, or they're rotating around and revolving around, right, and they've got to smack together in that proper orientation, if you start putting other couples and products, right, in the way, it now makes it more difficult for those reactants to move throughout the environment and run into each other, come in contact with each other, right? So at low concentrations, adding more concentration is great and speeds up the reaction, right? But once your environment is already full and jam-packed, if you're cramming for space, right, then it's no longer beneficial to continue to increase the concentration. You can actually inhibit and hinder your reaction rate. Also, besides having reactant and product concentrations, you can increase the concentration of the enzyme. And that will speed up the reaction rate, once again, to a point, right? So if all of your enzymes aren't busy, right, making matches and doing jobs, then adding more enzymes, adding more matchmakers into your reaction will speed up the process, okay? But if your limiting factor here isn't enzyme number, but if your limiting factor is availability of reactants, for example, having more matchmakers to kind of go in and help join won't do you any good if there's no reactants to join together, okay? So, and then once again, having extra concentration of enzyme, extra matchmakers in the way in the environment, if they don't have a job to do, they're just bulky and in the way and clogging up space that could be better used. Under enzymes, something we didn't consider in our initial reaction rates, under enzyme rates, we want to talk about pH. Okay, so once again, pH here, we're going to be looking at coming up is the concentration of H+ ions that are in a solution. And pH is going to have an effect on protein shape. Okay, so an enzyme is a protein, and it has this folded 3D structure, and we're going to be looking at that coming up in the macromolecule lecture. But it only has its proper shape and its proper function under a certain pH. So, you know how I said enzymes are specifically designed and tailored for a particular reaction. And so that enzyme has a particular pH range, the pH of the environment that it was designed to work in, that it best operates at. And if you put that enzyme in a different environment that it wasn't designed for, that it doesn't that it does not operate effectively or efficiently in, you're going to have very poor reaction rates. So for example here, enzymes that work, say, in your stomach, we'll talk about, say, pepsin is a digestive enzyme in the stomach, and pepsin works at an optimal pH of around 2, right? That's extremely low, okay? Our pH scale goes from essentially 1 right up to 14, and so 2 is on the extremely low end of the pH scale. So if you took pepsin and you took it outside of that acidic stomach environment and you put it into, say, just a regular blood environment with a pH of 7.4, okay, that enzyme is not going to operate. It's not going to do its job. It's not going to catalyze reactions under those conditions because it's not going to have the proper shape and function in that environment to do its job. Okay? So pH is important, and maintaining a proper pH balance is very important inside of your body, or all the enzymes in your body would stop working, which means you wouldn't be able to do any chemical reactions, which would mean death. So just a couple of examples of how important a single enzyme can be. If your body is incapable of performing a single reaction out of the hundreds of thousands of chemical reactions your body performs every day, that can cause major complications. So here's one of our little A&P in the real world blurbs. Like I said, I love to kind of bring these in and give you some real world handles on this information. So what happens if you have an enzyme deficiency? So if your enzyme's not working, or not functioning optimally, or your body, you have something wrong, your DNA mutation or something like that, and you don't produce this enzyme at all, then you can't catalyze the reaction. So, for example, Tay-Sachs disease is a enzyme deficiency, and what happens if it causes a accumulation of gangliosides in the brain, and eventually, if you can't get rid of the gangliosides, it ends up being toxic to the brain, and it usually causes death by around age 3. Also, if you've ever heard of the kind of the boy in the bubble, or somebody that's severely immunocompromised, a severe combined immunodeficiency syndrome is also caused by the lack of an enzyme, and so that adenosine deaminase there, if you don't have that, you basically don't have an immune system, okay? and with no immune system, then you have to basically live in the bubble or environment, or you're going to get some type of infection, likely to get an infection virus, something like that, and it'd be fatal. Then finally, our last example is probably the one you're most familiar with, and this is fetal ketonuria. If you have a child or you know an infant, one of the first things they do when you have a baby is they immediately take them and they do a test to see if the baby is able to process phenylalanine. So if you don't have this enzyme, you're not able to convert phenylalanine into tyrosine. And if you have a buildup of phenylalanine, it leads to mental retardation and seizures. And so you can avoid this by simply through diet, by simply not ingesting phenylalanine. And so that's where the baby, you see the baby formulas now that are usually more expensive, but we have these special baby formulas that say no PKA on them, right? And a lot of the infant stuff you'll see this, there is marked for infants with phenylketonuria. Right, and that's what they're trying to do is through diet, right, avoid the ingestion of phenylalanine so it doesn't lead to the seizures and mental retardation. So now we're going to kind of shift gears again here. We're going to move on to our next learning outcome, and we want to go back and revisit water. Okay, we're going to continue to revisit water throughout the course. Because your body is 70% water, right? All of these reactions we're talking about are happening in this aqueous environment, and so the properties of water are very important. So this time we want to focus on, mainly focus on reactions inside of your body and what your body is using, the properties of water that your body is taking advantage of. So the first thing reason that your body is kind of using water is that water absorbs heat without changing significantly in temperature itself. Okay, so that allows your body to basically use water as a heat sink. Okay, your cellular respiration, we're going through and we're burning lots of energy. There's lots of reactions going on in your body, and a byproduct of all of those reactions is going to be heat. Okay, these reactions that give off energy, part of that energy is going to be lost as heat. And so your body has to have a way of dealing with you basically being this giant nuclear reactor all the time and producing this heat. And it uses water to soak, like I said, as a heat sink to kind of soak that heat away from the body. Also, water carries heat with it when it changes from liquid to gas. Okay, so why is this important, right? Well, this is how your body keeps cool, right? So when you go to sweat, right, your body, the water is going to leave the surface of your skin, and it carries the heat with it. Okay, so that's going to, as it evaporates, it's actually going to cool your body because the heat is going to be transferred with it as it goes. Right, so that's a really important property. That's why sweating is effective for lowering your core body temperature. Also, water cushions and protects the body's structures. Okay, so we have all of your cells are filled with water, and we have water layers inside of our skin, and it gives us that because of bounce and buoyancy and that protection that the water provides. And then finally, water is going to act as a lubricant. Okay, so we don't want friction inside of our body. You've got lots of cells rubbing against each other. You've got all kinds of other interactions inside the body, and we don't want to lose energy and generate heat due to friction. So we make sure and use water as a lubricating source. The other part that we want to talk about while we're talking about water is hydration spheres. So we're going to be moving into talking about diffusion and osmosis here. And one of the driving forces here behind osmosis is going to be hydration spheres. So basically, when you put ions in a solution, so let's say we had a beaker of water, and we're going to put some table salt in it, right? Sodium chloride. We know that when we put the salt in the water that it's going to dissociate into ions, right? We're going to have a positively charged sodium and a negatively charged chlorine that are now floating around in the water, okay? So when we do that, because they are charged and the water molecules that we've put them in are also polar, the water's going to orient itself in a particular way. So the chlorine, right, that was negatively charged, right, is going to have all the positively charged hydrogens are going to want to turn their side, the hydrogen side is going to want to be turned towards the chlorine, which means it's going to want to put its negative side away from the chlorine. And then the opposite is going to be true when we look at what's going on with the sodium. So in the sodium, you're going to see that we want that the negative side, right, of the water is going to be turned, the oxygen side that's negative will be turned towards the sodium, right? And our hydrogens here are going to be where our positively charged hydrogen heads are going to be oriented. So these have opposite orientations, okay? So if you've ever wondered why do you throw salt in the water, right? Why does it disassociate into these ions? Why doesn't it just snap back together into sodium chloride and be salt floating around in the water? Why does it dissolve? Right? Well, it's because once these ions get into the water and then once they break apart, the polar nature of water pulls them apart, right? And once they're pulled apart, they get surrounded in these hydration spheres. So now there's these bubbles, these wrapped layers around them. So now anytime a negatively charged chlorine, right, comes, it has all negatives out here on its surface, right? So, and then on the outside, these sodiums, right, now we have all positives out here. So once these get water wrapped in these individual balls, then these hydration spheres kind of get stuck together, right? But the chlorine and the sodium are never able to come back in contact with each other to potentially rejoin, right? As long as the water's present, because the water has them surrounded, has them water wrapped in a hydration sphere. Ions that are, if an ion that is not wrapped in water, right? We're showing you two ions here that are completely surrounded, okay? But if this ion was not completely wrapped in water and it had some gaps where some more water would be attracted, okay? If we had other loose waters, right, that were floating around out here in the beaker, right, other loose waters would come in here and line up into the slot if this wrapping wasn't complete. Okay? And that's going to be important later on when we look at osmosis, because this is one of those driving forces behind osmosis. So we'll come back to this a little later. So I just showed you that water, right, being polar, is a great solvent. We talked about it back when we talked about solutions, right? We mentioned water as a universal solvent, and it had great properties because of it being polar. Here's where we're going to see this again, that water is a great solvent for a hydrophilic solute, right? That means it's going to be water-loving, right? That's what hydrophilic means. It also means that it's going to be partially charged, or it is going to be polar, right? And so this is where we get the idea that like dissolves like. So what I mean by that, like dissolves like, is that water is polar, right? So therefore, water is going to dissolve polar, right, anionic compounds and solutes. So now let's start to talk about acids and bases, okay? So some of our solutions that we have, we can talk about being acidic or basic. And so let's start with acids, okay? An acid is an electrolyte, okay? So remember that was a charged particle. We put ions, right, into water, right? We have charged particles in the water. We said that that is now an electrolyte. So acids are an electrolyte because they're going to release this H plus, this charged particle, into the solution. And so they are proton donors, right? H plus, right? Hydrogen, proton donor. And so they're going to release the H plus ions out into the the solution. If we measure the concentration of H plus, okay, that is going to determine our acidity. Right? And this is what we refer to as pH. Okay, that concentration of H plus ions. So in the bottom left here, we have HCl, that's hydrochloric acid. And if you put hydrochloric acid, when you add it to water, it disassociates into H plus and Cl negative. And that, if you put, that's going to give you a high concentration of H plus ions in solution. Right? Just the opposite is to look at bases. Okay? So bases are also electrolytes. Okay? Why are they electrolytes? Because they ionize, dissociate in water, and are going to put charged particles into the water. Okay? Except the charged particle that is being put into the water here is a base releases OH negative or a hydroxyl ion. Okay? So acids released H plus, bases release OH minus. So the OH minus concentration here, if you were to measure that concentration, is what's known as alkalinity. Now we usually talk about things in concentration of H plus ions. We usually refer to things in pH. Okay, alkalinity is more rarely measured, but if you're doing tests, like say for your swimming pool, for example, you've probably done an alkalinity test before. And what you're measuring there is the concentration of OH minus, the concentration of those hydroxyl ions that are present in the water. So you can see here on the bottom, NaOH is sodium hydroxide. It's a strong base. And if you take that strong base and you put it into water, it's going to disassociate into Na plus, sodium, and our hydroxyl, our OH minus. Okay. Earlier I mentioned if you take a acid and a base and you mix them together, okay, meaning you had the H plus ions here from that were from your acid, okay, and you take your OH minus here that were from your base, okay, and you add those together, you're going to get water, right? Because you're adding H plus and OH minus, and that is H2O, right? And that is water. So the pH of solutions, as I mentioned, is determined by the concentration of H plus ions. Okay, I just wrote it on the last slide. pH is concentration of H plus ions. So we have a scale of pH that I'm going to show you that goes from 1 to 14. And in the center of our scale, around at 7 here, okay, we have water. Okay, so water is in our neutral pH. It's in the sitting right in the middle, and so it's going to have a 7 pH. So if we have a solution that has an abundance of H plus ions, we say that it is an acid. And if it has an abundance of OH minus, we say that it is a base, right? Just as we just introduced. Here's our scale that I was talking about, okay? And this is a base 10, a logarithmic scale, okay? So notice here that as we go from 1 to 2, for example, okay, that we're talking about 10 to the minus 1 and 10 to the minus 2, okay? So we're talking about the difference in pH 1 and pH 2 here is a tenfold change. We're talking about an entire decimal place here, okay? So as we're going through, say, a difference here in 1 pH, so we'll say the difference in pH 1 and pH 2, a single digit here, would be the same as saying comparing 1 million H plus ions to 10 million H plus ions, right? It's a huge difference. Okay, so people say, oh, well, the pH is 1, or pH was 2, it was 3, not a big deal, right? It's close. No, it's a massive deal. It's a huge miscalculation, okay? So pH is on a logarithmic scale, which means minor changes in the number of pH is actually massive changes in the amount of H plus ion concentration, okay? So that's what I was saying. You're talking about 1 million H plus ions versus 10 million H plus ions, right? And that difference only gets greater, right, as we go up in scale, right? But if we're talking about that decimal place, that tenfold difference. So, also, this is a negative logarithm scale, right? And the lower pH means higher H plus concentration, okay? Once again, a higher H plus concentration means a lower pH number, okay? So that means that over here, the H plus concentration, right, the more, right? So this is 10 to the 0. Okay, this is the highest. Okay, down here at the bottom is 10 to the negative 14th. Okay, so if this is 1, down here we're talking about 1, right, with 14 zeros. With 14 zeros before it. Okay, so don't be confused in the way the numbers that are written, right? When we're talking about 10 to the negative 14, that's the really small number. 10 to the 0, right? That's the positive number, right? Going from 10 here all the way down. So that means that a lower H plus concentration means that you actually have a higher pH number, and then that means that you're more basic, okay? So lower H plus means higher pH, and that is basic. So since we said that changes in pH, right, very small changes on the pH scale, are actually massive changes in the amount of H plus concentration, right? And pH, right, the enzymes in your body are tailored to operate at a specific pH. And your body takes great care to resist any rapid changes in pH, right? Because a rapid change in pH would destroy your enzymes. If you don't have any enzymes, you can't do any chemical reactions. And without any chemical reactions, that would be fatal, right? So your body has this buffer system in place, and this buffer is going to try to prevent a rapid shift in pH, right? So buffers resist or prevent these rapid shifts in pH. And your body does this by keeping weak acids and bases around, and they help maintain this equilibrium. So basically, let's assume that if your pH is rising, okay, so when the pH rises, right, that actually means that your H plus concentration, right, is actually low. So if your pH starts to rise, what you want to do to counter this, kind of in that negative feedback loop style, right, to kind of, if the pH starts to rise and you want to bring it back to the set point, what you need to do is release some H plus ions into the solution, okay? That's going to increase the H plus concentration, therefore lowering the pH, and it's going to bring that balance back down to that set point, right, where you're trying to maintain that homeostatic balance and keep it inside that green range. On the opposite side, if the pH starts to fall, okay, so if the pH is falling, right, what that actually means is that our H plus concentration is now increasing, okay? So how are you going to counter that? Well, you need to actually take H plus, right, or you need to take H plus out of the solution, okay? So you can do that by, say, if you put in OH negative, right, the base, right, puts OH negative out there, then the hydrogen is going to bond to it, it's going to create water, and it's going to remove that H plus from the system. Okay? So at the top, you can see your blood pH levels, okay, and your normal and happy blood pH here is at 7.4. Okay, normal blood pH, hopefully there you can read that, is at 7.4. When you get above 7.45 or below 7.35, okay, so we're talking about plus or minus here 0.05 change in pH, okay? This is when your body starts to freak out and respond, right? This is that green homeostatic range is about plus or minus 0.5. If you get outside of that, your body's going to start to respond and try to correct the problem, right? It's going to kind of go into panic mode. So when you go above 7.4, okay, you're becoming too basic, okay? And if you go below 7.35, right, you're becoming too acidic, okay? So all the way down, if you enter, say, acidosis, okay, that's going to be this whole range from 7.35 down to 7.0. And that's that range where your body's going to be fighting to increase pH, right? That's going to be this bottom example here, right? So we were talking about in acidosis here. Okay, this is this bottom situation. So you want to bind up those H plus ions and get them out of there as quickly as possible, right? And the opposite is true on the upper end of the scale. So this is the range, right, that your body can handle, that the buffer system works, okay? What happens when you get outside of 7, okay, or above 7.8, right? Well, now you've reached a range where this is probably fatal, okay? So this is for buffering. So 0.5 here is your buffering capacity, okay? But plus or minus as little as 0.4, right, can be fatal. So is there a big difference in pH 7 and pH 8? Absolutely. It's the difference in you being alive or being dead, okay? So make sure, even though they're tiny numbers, that you understand it's a logarithmic scale, which means we're talking about massive ion concentration. And also, this is extremely important to your body, right, to life. So here's showing you how that buffer system works, right? Because we were just talking about at the bottom here, we're looking at releasing H plus into the solution or binding H plus out of the solution to help counter the pH change. So here's giving you the actual biological system, and we can look at carbonic acid in the blood as an example of this. So if you have H2CO3, you have this carbonic acid in your blood. And if you need more H plus, right, released into your system, right, to increase that H plus concentration, right? So if you want to do H plus, right, we want to increase that, which means that our pH, right, is then going to decrease. Okay, then we can shift this in this direction, which is going to give us more available H plus. Okay? This is a reversible chemical reaction, right? So what does that mean? Okay, I'm not going to write it on the screen, so I don't want to confuse you, but that means that I could use the backwards arrow and go the other way, okay? So if I needed to raise my pH, if I needed to lower my H plus concentration, right, I could take those H plus ions out, right, by providing HCO3 negative, right, to the solution. I could actually take that H plus out and reform the carbonic acid and remove that H plus from the solution. So having these little buffering systems, these reversible reactions where things can flip between the carbonic acid and having the free H plus in solution gives your body a way to resist and to kind of fight and maintain these proper pH levels. Finally, how do we know what pH is? Well, so in the lab, we use a pH meter. It's a little probe that we can actually put in the solution, and it will tell us exactly what the H plus concentration is in that solution, so that we can then do a little calculation and know what the pH is. Some kind of old school pH indicators and some other ones that you might be aware of and have seen before is litmus paper. So you can see an example of it on the top. And when you go in our laboratory section, you may see a couple examples where they show litmus paper and its function and just indicating whether something is acidic or basic. So if in the center there is, the center beaker is water. So if you put these two pieces of litmus paper, they make a red paper and a blue paper, and you put them in water, which is neutral, and nothing changes color. When you put the blue paper into an acidic mixture, you can see on the left there that the blue paper then turned red, meaning that was an acidic mixture. And then on the right, you can see that the red paper turned blue, right? And blue meaning that is a basic solution. We have more complex indicators than just kind of the yes/no, acidic, basic, like you see with the pool test strips there, where they kind of have this tricolor system. You can dip it in, and in the laboratory, these are the dip strips that we use quickly for experiments, just to check the pH of a solution if you don't want to go through the most accurate process of actually going through and checking it with a meter. Finally, we were able to make these pH pH indicators, different solutions for a pH indicator. And there's actually one kind of do the third grade science experiment here. And you can make an indicator from cabbage juice. Okay, so if you take red cabbage and if you boil it, the pigments in red cabbage actually respond, and the hydrogens actually bond here to the pigment. And depending on how saturated the pigment is with hydrogen ions, it's going to change the color here of the cabbage juice, which means it's a great indicator since it changes color depending on hydrogen plus concentration, H plus concentration. We can use it as a great indicator. That is all for this lecture, so join me back next time.